charge, 1. So skyrmion number is 1, and the electric charge is also 1. So they are the same. So actually, we know that so the previous slide tells us that the number of zero mole is very crucial in determining the skyrmion charge. So what about if we consider the case in bilayer graphene? So if we can show, okay, there are also zero mole in bilayer graphene, we can also conclude how many charge from the skyrmion texture. So again, we will encounter this kind of problem in which the momentum is no longer linear, but it's in quadratic. So the mass also has a vortex here. So it's it's not clear how to show that actually there 1 zero mole or 2 zero mole or no zero mole. So okay, so this the first two terms are responsible for the bilayer graphene quadratic band touching, and the later two are for the vortices. So actually, we can do a Fourier transform to reinterpret this Hamiltonian. So after we do the Fourier transform, these two parts become a vortex, a double vortex in momentum space, because once you do a Fourier transform, this becomes cosine 2k. And this is a sine. And here, the vortex part, because we do some linear approximation, so these two parts in momentum space become a linear operator. So it's actually the same Hamiltonian as discussed by Yakib and Rossi. So in real space, it's a quadratic band touching and a vortex in real space. But in momentum space, it's a double vortex in momentum space. But the linear in derivative. So again, by Yakib theorem, we can conclude that there are 2 zeros. So in a simple words, so in the bilayer case, the charge will become double as well. So in single layer, we have charge 1e for skyrmion, but in 2 layer, we have charge 2e for double layers. Just so the double of the charge actually come from we change from linear band touching to quadratic band touching. So let me say another, because in the beginning I emphasized the importance of the magnetic field. So what about is there any zero mole again in the presence of the magnetic field? So in which previously in the HD we only have linear momentum, but in the presence of magnetic field, the Dirac Hamiltonian becomes this form. So if m is 0, so this will just give you the spectrum of the Landau level in graphene. So you have zero energy Landau level, and the first Landau level, second Landau level. The energy follow as a function of square root of b. But what about when we consider a vortex in this mass term? So actually, we can apply a simple unitary transformation that kill the vortex. So actually, the cost we pay is actually we insert another flux into one of the component here. So there's no vortex here anymore. And okay, so because I don't have so much time, so actually we can do some deformation that change a Corbino geometry into a ribbon, and from a ribbon we change it into a simple stripe. So in which we have to connect the upper edge with the lower edge. So where the vortex goes? So because the vortex is hidden in this little a here. So the little a here is actually equivalent to a gauge field, a large gauge field. So the large gauge field here is actually does not depend on, because of the geometry, it doesn't depend on the coordinate. So the vortices here is hidden in this Q. So when Q is 1, it's a single vortex. When Q is 2, it's a double vortex. So what happened to this vortex and mass order parameter? So actually, because previously without the vortex, without the mass, and the vortex, without the mass, so you will have zero lambda level here from one component and 2 by 2 component, and the other zero lambda level from the other 2 by 2 component. And the zero's lambda level wave function is written as this one. So it's just a simple harmonic oscillator times some plane wave. And here, so you have similar form for another component. So the only exception, or the place where the vortex enter is actually, it changed the plane wave here. So when you have vortex here, the momentum is shift. So because of the shift, when the mass enter your problem, the mass is actually just to couple the state. Okay. So because of the shift, because without the shift, this one will couple with this one couple with this one. So after the couple, there's no longer any zero energy more, because when zero encounter not zero, just become split. But with this little shift carried by the vortex, this one will have to couple with this one, and this one will couple with this one. So in the end, the zero lambda level here and the zero lambda here has no one to couple to. So there will be the zero energy state, zero energy vortex state in the end when the uniform magnetic field is present. So again, we can show that the index theorem, the Yakib index, in the presence of constant magnetic field, is not changed. So the index is actually the number of flux times the number of the orbital degeneracy. Let me explain a little bit. So the first number is actually controlled by this one. So it is the number of the Wanning number, or number of the vortices. And the second number is actually a single layer or two layer, because in single layer we only have one zero, and zero energy lambda level. And in double layer we have two zero energy lambda level. So these two numbers times together give you the number of zero mole and the index theorem. So okay, so because I only have 10 minutes left. So actually, when we consider the spin, the story is quite simple, because previously we only discussed the 4x4 Hamiltonian, but when we consider the spin, it will have a 2 4x4. So the end, so whether the skyrmion is charged or not, it depends on your decomposition. So in some cases, we have a copy of two skyrmion, so in which n is positive and this n is positive. But in other cases, you will have a 4x4 component, which is n, and the second half is minus n, because the electric charge is equivalent to the skyrmion charge. So in that case, the charge will cancel with each other. So this is already shown by Sentier and Glover. So actually, the trick they do is actually is just integrate out the fermion. So they find that in the A by A component, it's actually in this case you consider a graphene Hamiltonian coupled to Chem and Lee Hamiltonian, Chem and Lee masses. So in this case, it's your two 4x4 component. Each one give you E charge. So in the end, the total charge is 2E. And in my paper in 2012, we consider different contexts. In a more general context, we consider two-layer graphene, in which you have quadratic band touching instead of a linear band touching. So we don't know whether we can apply the gradient expansion trick. But in the end, we find that actually the charge is double, because here is the A by A matrix. So whenever this gives you identity, A by A matrix take trace is 8. Divided by 2 is 4. So in this case, the current skyrmion is the electric charge is 4E. So what's the difference between you have charge and you don't have charge? Actually, we need to consider the other two elements here. Actually, in several years ago, Claude Chamon has a table for this 5 matrices. So actually, we can find that actually the case that in the end give you non-zero charge is these two masses are superconducting. in the case that the skyrmion is not charged, these two masses are also insulating. So all the 5 masses are insulating here. So that gives you Q equals 0 charge. So in the end, these two cases just corresponding to these two classes. So in the case with charge, you actually is equivalent to is a trivial copy of 2 skyrmion Hamiltonian. But in the case that the Q is 0, it is corresponding to the, you have one component is skyrmion, the other component is anti-skyrmion. So in the end, the charge is cancelled. So this is just another paper that, because in the end, once you show, okay, you can find a charge skyrmion, you can actually write down another topological term, which is the West-Wino-Witten term, which involves all the 5 order parameters. So you actually show that the number of layers Q is actually describe your degree of the band touching. So I already showed that Q is 2, your charge will double. And they also use a very complicated diagram calculation to show that actually the Q will also appear in this place. So that means your skyrmion will have a charge proportional to the Q here. So in the end, I'm almost finished. So this is something that I'm not familiar about. I find out actually in the morning, Professor Gu also mentioned this kind of mechanism. So actually, because we have in the spin in the graphene, if we consider spin, we have 8 by 8 matrices to describe our Hamiltonian, and in that case we have 5 matrices to describe the order parameter. So actually, if we so the premise is what I say is actually we can form a skyrmion texture of these 3 masses, and this skyrmion texture can carry charge. So actually, there's one interesting story is that if those bosonic degree of freedom which carry charge, and somehow they start to condensate, you will go into the superconducting state, which is not BCS. So this will be, I think, I look forward to the progress in the future. And okay, so this is my conclusion. So I find out how to find a generalized index for the vortex in various Dirac systems. And from the 0 mode, actually, we can conclude that we can, without doing the complicated diagram technique, we can conclude there will be a level n WCW term in this system. But that also implies a non-trivial quantum phase transition. So in the end, so whether this non-BCS mechanism for superconductivity is really relevant to real material like cuprate, that's something we are looking forward to. Thank you.
A few minutes.
So can you show the West-Witten term that Sophia Sashlik calculated again?
Yes.
Yeah, this one. So this vector n, what's the physical meaning of vector n?
N is the
that's the nail VBS or something else.
yes. N is you have 5 indices.
Yeah.
So 3 of them for this one. So neo state, you need 3n. And I mean, it's a 5-dimensional vector. In 3 of them, I mean, it's a 5-dimensional. So if you point down to the neo, so 3 of them represent the neo order, and the other 2 of them represent the VBS order. So 2.
Bilayer.
It's a bilayer, but they only consider the low energy honeycomb. So the other 2 they neglected. So you need a 5n here. N1, N2, N3 for here, N4, N5 for here.
And what's Q again?
Q is I mean when Q is 1, just graphene.
Right.
Graphene.
Oh, Q is a layer.
It's layer, but it's show up in the spectrum. When Q is 1, it's a linear spectrum, and Q is 2 is quadratic band touching. So we can also have 3A, which corresponding to Q is 3. Yes. But here, the point is this case, in the background, there's a strong magnetic field out of the plane.
Any more questions?
Yes.
Yeah, please.
So in our last slides, I'm wondering if we think about this skyrmion carry non-trivial topological charging, it's still a boson or the state distance actually. So typically, I think if there are zero modes in the skyrmion on the boson would be any.
I think the statistics will be implied by. I'm not sure. Actually, I'm not expert on.
Because there's a simple example, like if you think about P plus IP or D plus ID superconductivity, the vortex is going to trap zero mode, there's a statistics change, so the vortex become any.
Yeah. Comment about that question. So actually, skyrmion is a local configuration. So skyrmion cannot carry any fractional charge. The vortex is a non-local object. It has a range problem. Can carry fractional charge, but skyrmion cannot. Skyrmion can only carry either firm or neutron.
Yes. Yeah, because actually the fractional charge appear in this talk.
Here I'm thinking about this skyrmion is something like this Z3, right? It's not really.
Oh, that's a vortex. That's not skyrmion. The Z3 is like it's a Z3 vortex.
Yeah. So
skyrmion is always a vortex, anti-vortex bounded state. That's already a local. When it's a local object, it cannot carry the fractional charge. It can only carry charge 1 and charge 2 and charge 3.
I see. So it's already bound state.
Yeah, the bound state.
It's a bound state.
So they can also condense.
That part I have no idea. I think Professor Gu has a more clear picture about how to condensate those skyrmions.
Yeah, actually, in my picture, kind of slightly different because it's kind of like the skyrmion current and the charge current interaction. So it's just this skyrmion is not really carry charge, just like before. Maybe it's easier to carry, but yeah. So it's possible that skyrmion can also carry charge and condense by itself, but in that case, also we might worry about the strong computing control. Because if the strong computing is not really complex.
Okay. Thank you.
Any further question or discussion? If not, I thank the speaker again.